Hi guys, today we are going to be going over electric fields and electric field lines. We're going to be going over what exactly those are, how to solve for electric fields, and how to draw an electric field line. So first, let's talk about what exactly is an electric field. An electric field is an interaction between two objects without any physical connection. Electric fields are caused by electric charges. So to visualize this, let's watch a short clip. The big metal thing in the center is a charged sphere, and that is a piece of string attached to the ruler, and you can see that the string is not coming even close to the charged sphere and kind of keeping away from it at the same time. So as you can see, there's no contact between the string and the charged sphere. However, there definitely still is interaction, and this is what an electric field is. Now the question is, how do we calculate an electric field? Well, the equation is given E equals F over Q, or E equals K times the absolute value of Q over R squared. Now, K is the electrostatic constant and is equal to 8.99 times 10 to the 9 Newton meters squared over Coulomb squared. For these other variables, E is the electric field, F is the electric force, E is measured in newtons per over Coulomb, and F is measured in newtons. And R is the distance Q is from the charge, and that's measured in meters. And Q is the test charge, which is a positive charge that is placed in the electric field. So now that we know the equation, we're going to do a practice problem. The problem states, calculate the strength and direction of the electric field E due to a point charge of 2 nanocoulombs at a distance of 5 millimeters from the charge. My favorite trick when doing physics problems is to memorize all of the SI units for each variable, so that when I'm given those SI units in a problem, I know exactly what variable they plug into, so I can choose my equation off the equation sheet. So we know that coulombs relates to charge, and meters relates to distance, so we know that we should probably use the electric field equation. So, knowing that Q equals 2 nanocoulombs, R equals 5 millimeters, and K equals our constant 8.99 times 10 to the 9th. So we also have to remember that we are measuring in coulombs and meters when we're plugging into the electric field equation. So you want to transfer nanocoulombs and millimeters into coulombs and meters, and then plug it into the equation. Go ahead and hit pause and try it out for yourself. So here is the formula with all the numbers plugged in and the answer you should have gotten. If you got something else, go back and try it again or look up some other practice problems. So now we ask the question, what do electric fields look like? As we saw in the video earlier, we couldn't really see anything, any physical connection between the charged sphere and the string. So how are we going to illustrate these when we draw them in diagrams? So there are a couple of basic rules that we want to follow. Number one is that an electric field extends from an object in all directions. So basically that means that an electric field is not only going to come out from the top of an object or from the side of a particle or whatever, it's going to come from all different angles. To represent these electric fields, we draw diagrams like the ones below. The lines are considered the electric field lines. And we'll go more in depth about the arrows and the closeness of the arrows and what that represents in the next slide. So now let's get on to some basic steps for drawing electric fields. Number one, field lines must begin on positive charges and end on negative charges. The ones you see in the picture below are actually hypothetical isolated charges and go on for infinity and therefore have no beginning or end. But just know that in the real world, field lines begin on positive and end on negative charges. The closer the lines, the stronger the field. Number three, the number of field lines is proportional to the magnitude of the electric field. Number four, arrows point in means that there's a negative charge. If the arrows point out, it means there's a positive charge. Number five, direction of magnetic field is tangent to the field line at any point. And number 6, field lines can never cross. So let's take a look at these rules in comparison to the pictures below. The picture number, or letter A, has arrows pointing out from the charge, which means that the charge is positive. B has the arrows pointing in towards the charge, therefore the charge is negative. And then finally on C, you can see that there are a lot more lines coming into the charge, or the center, and that means that the magnitude is greater and the field is stronger. So you can compare that B and C, they're both negative, but C is going to be a much larger charge. So now you might ask, well, what happens if I bring in a positive and a negative charge and put them close to each other, or a positive and a positive, or a negative and a negative? Well, there's some rules with that too. You probably already know that opposites are going to attract, and the same charges are going to repel each other. So you can see that the same charges on the top picture are going to repel each other. This one happens to be 2 negative charges, but is the exact same for 2 positive charges. And those 2 charges are also of the same magnitude. So they're equal charges, both negative, and they repel. And you can see on picture B 2 charges that are of the same magnitude, but one's positive and one negative, and you can see that they attract. And one big picture thing here that I want you guys to get is that electric field lines cannot cross. So let's go over what we just learned. An electric field is going to be an interaction between 2 objects without physical contact, and it's caused by charges. It's mathematically calculated by the electric field equals force of the field over Q, the positive test charge. And field lines represent the strength and charge of electric field. More lines means there's greater strength. If the arrows are pointing in, it's a negative charge, pointing out positive charge, and field lines cannot cross. I hope this really helps.